Perfect. Okay, so this is going over how to compile the kernel. This is your final project. I am doing this earlier than what I'm supposed to. Supposed to give you guys 1 week to do it. Yeah, right. So I'm going to give you guys more time than that to do it. This is written up in script form. This is how you do it for Red Hat Fedora only. You would do it a different way for the other Linux distributions, but for Red Hat, this is how you do it. Okay. One of the gotchas here is you must be root ahead of time. So on this, so you could do a test where see if they're root and automatically make them change into root, like we had before with the LAMP server, for instance. And we did that here. So if you wanted to, you could literally copy and paste this out or whatever. I ran these commands individually, though. I didn't run it as a script last night, so I have not tested it running as a script. But literally, I would tab all these over as part of this if statement. So, and that's probably a good thing. Yeah, this one's important. You have to put the quotes around it. I'm going to go over these in just a second. Now, the fun part about this is that this routine for what you do changes like every daggone time I do this. So it seems like about every 3 months or so, they change how you compile the kernel. That didn't used to be the case, but now it seems to be the case. So, very frustrating, but that's the way it is. Here I'm actually querying the person for asking them. I'll show you guys in a second here. I'm just going to break this down here real quick. And make gconfig, and then what would follow after that would be those series of commands. And some of the stuff, honestly, you couldn't do it all as one script, just because the order in which you have to do things just isn't going to work out. And then this command is no longer necessary here, which I need to give that a space there. Alright, so I went ahead and commented it out too. Okay, so let me break this down real quick. You would need to be root ahead of time, of course. You're going to cd into root. Actually, before I do that real quick, let's just copy this whole thing down here where it for the else statement, and then you're going to write this up yourselves, and then you're going to actually do the kernel compiling. And it's actually a lot more complex than just a script, so give me a moment. And so basically what this does, why do we compile the kernel? Well, one of the reasons we compile the kernel is that it lets us make our programs run a whole lot faster. So and that's a pretty important thing, actually, as it turns out. And this is how you would do it, of course, just for Fedora only. Let's see. This will be kernel.sh. Alright. Okay, so, and the reason why you would do this, compile kernel, is you can essentially, okay, let's go over what the kernel is first. Kernel is core your operating system. It is what makes up your whole operating system. It's the central part of it. Literally, all the stuff, every time you enter a shell command, anytime you drag and drop a file, all that has to go through the kernel. Everything does. The reason why is the kernel is literally your drivers that interface with your hardware and things like this nature, and they actually interface with the higher up commands and layers of software that make up your operating system. So quite literally, the kernel is your operating system at the most fundamental level. So the kernel literally figures out, when you say, I'm going to copy this file from here to here, it literally figures out, okay, I'm going to use this routine to read from the CD literally move the laser, in and out and read that device. And then I'm going to take that data and I'm going to send it in this format as I translate into this format here. I'm going to take that centralized format and then I'm going to write it out into the ones and zeros in the magnetic form of the hard drive as it spins. And I'm going to do that. Literally, that's what the kernel does. So, literally takes, and then, so, like, you type in, like, C, copy or whatever, and it's just this one little command, right? But underneath the hood, the kernel is doing tons of commands to do that. So it makes it really easy for us to do things with the computer without having to get super technical about every little thing we're having to do and trying to have to think about it in detail as far as that goes. So it just makes life easier. But it's what sits underneath the hood and actually does the real work. It's the workhorse of the operating system. So what we can do, though, is if we know how to compile a kernel, we can remove a bunch of junk we don't need. Like, for instance, we probably don't need a television card on your computer where you turn your computer into reading the signals from a broadcast television station to pick it up on your computer. You can get one of those cards and do that on a computer. But most likely you don't have that on your server. Other things you probably don't have on your server: game controllers, things of this nature. I can go down the line. There's lots of things you probably don't have on your server that you wouldn't need, or even on your local machine, client side. So this means if you don't need it, you don't have to have it in your kernel, right? So literally, by recompiling the kernel, we can actually remove a bunch of stuff that we don't need in there, and thus allowing you to shrink down the size of the kernel, make it smaller. And if you can make it smaller, it makes it run faster because it has less code to skip through. Does that make sense? So the more junk we remove that we don't need, the smaller we can make that kernel, and we can make it run quite a bit faster. There's another thing you can do too, is you can optimize compile the kernel for your computer. Now, I'll show you how to do it, but I'll show you how to do it. But basically what you can do is, I'll go through different compiling levels. 0 means no compiling at all. This is things like webmin or shell scripts would be 0 compiled, meaning they run on everything, because there's no architecture specific thing at all. Python's another good example of that. Python scripts would be, or Perl scripts or whatever. Optimization 1 is going to compile it for a set of architectures. It's not hardly used because it's not very efficient. So as I go down the line of these different compiling optimizations levels here, it gets faster and faster for the programs. Also, they get bigger and bigger in size for the programs, but it's minimal, really. It's just not even worth discussing how small it is, really. Oh no, it may be 300 kilobits bigger. Oh no, it's no big deal for the whole kernel, and the kernel is like 25 megs or something like that. It's like, wow, yay, extra 300 kilobytes. Oh no, it's kind of one of those deals. It's not even worth talking about. But optimization 1 is not used that much because it's just not fast compared to optimization 2. Optimization 2 is what's used for most programs. If you download these RPMs when you do your yum install or anything like that, you're getting optimization level 2 for all your programs. This goes for certain architectures like i386 or x86-64, etc. Those are architecture specific, so you have to get the ones for your architecture. But it does run faster because it is compiled to take advantage of those architectures. Does that make sense? Architecture optimization levels 3 and 4 can only run on the machine it's compiled on and not on any other computers, because it's going to be specific to that computer, meaning it's going to actually compile it down to take advantage of the specific hardware in that system specifically. And optimization level 4 is the highest one, and that's where it's going to take the most advantage of it. What it starts doing is it goes down to assembly level and goes, okay, I'm going to use these routines of the assembly because this most closely matches the hardware. So as it does that more and more, at these higher and higher levels, you get better and better speed. You can get anywhere from 2 to 4 times increase in your speed of your whole computer by compiling down the kernel and changing the optimization levels. That's a huge deal. On a game engine, I was able to get it to go, by compiling the game engine itself plus the kernel, I was able to make it run about 16 times faster overall. So just a point in fact of why you would care on doing this stuff. You can also do this with servers too. Since these servers on Linux are open source, you can literally download the source code, optimize, compile them, and actually make them run significantly faster. You might be going, well, why do I care? Well, let's put it this way. If you can sit there and make computers run 16 times faster, that'd be the equivalent of buying 16 additional computers, not counting the additional cost of electricity to run 16 more computers and things of this nature, because you essentially have just saved a ridiculous large amount of money by optimized compiling down the servers and the kernel. So that's why you're learning it. It's actually a big deal. You're not going to get compiled kernels from manufacturer. It's something only individuals at companies would do, or at home, or whatever. I used to do it for years where I'd optimize compile. But case in fact, I had a game engine that was running 60 frames per second, which is target frame rate, right? Both on Windows and Linux, it ran 60 frames a second. Optimize, compile the kernel and the game engine, not even the support libraries for the game engine, just the game engine itself. And it was doing 1,000 frames per second. On the upper end, the worst it ever did was 333 frames per second. So it's significant increase in speed. Yeah, just as a performance test type thing, you could expect to get the same kind of thing from a server like Apache or something of that nature. What's that? Yes, but you can't do this on Microsoft because it's closed source. So you don't even have access to the source code, so therefore you can't even do this. Most people on Microsoft don't even have a clue what a kernel is, type thing. When you get to Linux, you learn that there's a lot more stuff. You don't realize how much you don't know until you get on Linux about computers and operating systems, period. That's once you get on Linux, you start learning a whole lot about computing that you didn't even begin to know because you couldn't even access it in Windows. Whereas on Linux, you can access it, and so therefore the possibilities erupt, and things you can do gets crazy on Linux. So there's really no ceiling on Linux as to what you can or can't do. You can do anything you want. The question is, do you know enough to do it? Is the question at hand. So for this reason, there is significant amounts of more information that you could actually know that you wouldn't actually encounter normally. So that's literally what we're doing. We're going to actually go through and download the kernel source from Red Hat. I'm getting one specific for Red Hat Fedora, so that way it works nicely and happily with us. Sometimes it does, sometimes it doesn't. I did it last night. I compiled this whole kernel and everything and made it work. Now I'm going to tell you right now, I used to do this on a regular basis, and I could do it in a matter of hours or something like that. I've had previous classes where not a single student made it work the entire quarter for from week 7 all the way through week 11. No one could get it work. I've had other times where all the class got to work in the first week or so. It just depends on what problems you run into and whatnot. I didn't run into squat for problems here. And then how well you can actually work through those problems. And, typically students that run into problems can't work through them very well. So I did back when. I ran into problems back when, and I worked through them. So can I do it? Yes, and I've already done it. So I'll even show you in the video. So yeah, it's done. So no joke. Let's look at, since I can't download it, I needed to do this ahead of time anyways last night. But so what I want to do is I want to be root and then cd into that home directory, and then I'm going to use my yum downloader -- source space kernel to actually download the source of the kernel. If I wasn't doing this, I would go to www.kernel.org and download the kernel source, unzip it. Right. First of all, I'd copy it into the /usr/src/kernels folder, unzip it there, and then create my symbolic link. But we're going to do some other things instead, since we're doing Red Hat Fedora. We're going to use the yum downloader. We're going to use we need to install the RPM dev tools. Why RPM devs? Because we actually have to develop an RPM. This is the same process that you would go through if you were writing a program and you wanted to release it as an RPM to be downloaded by other people to install it. That's essentially what we're doing here with this RPM. So we got to have the RPM dev tools. RPM space -UHV. All right, the RPM here is the RPM for the install command. This is prior to yum. This is how we used to do it back in the day. And this is how we install a particular one. Now, this is going to be installing from the local location of where we're at on the hard drive and not from the internet, okay, for this RPM command here. So literally what we're saying kernel star or whatever, that's because that's a kernel that got downloaded from the yum downloader. And it's going to be there. Let me show you. Yeah, www.kernel, not kernel source, it's www.kernel.org. And that is where the Linux kernel is. That's the group that actually develops it. And it's a worldwide effort. I actually took a course from Tim Toso. Is it Kim or Tim? Tim. I don't know. It's one of the two. Can't remember. It's been years. But I went to the first 4 Linux conventions that existed in the United States back in the day. They all 4 were here in Atlanta. And I took a course from him. He was from MIT. He started his PhD at age 16. He's a really smart dude. And I understood about half of that lesson of that course that he provided for us. But it was over the kernel and how they developed the kernel and all the parts of the kernel for development and how to code it and such. Pretty deep stuff. And he said that he was an idiot compared to Linus Torvalds. So if you want to imagine, Linus Torvalds is probably one of the smartest people alive today, in all honesty. So that's who's developing your kernel, basically. Some of the smartest people in the world, quite frankly, are developing it. So it's a big deal. If we go from here, assuming I can't probably access this graphically, starting to think about it. What am I thinking? No, I can't do that because I would need to be root privileged to see that folder. Right, so that's not going to work out for me. So I'm going to have to do this through command line. So let me cd into root. And there we are. See, here's the kernel source code that was downloaded. See that? So when I did the yum downloader, this is what downloaded. So there's my kernel version and everything. And of course, it's a des.src because that's a source RPM. Source RPMs are always the src, like this. And then you can build the actual application on your computer from the source code, from the RPM, and it builds a binary RPM. The binary RPMs that you download, though, are op level 2. Okay. You don't get the same speed. Okay. So here I am, and I'm telling it to upgrade my source code. All right. So if it wasn't installed beforehand, it's going to get upgraded. That's what the -U is. If I'm installing it, it's -I, lowercase I, but if I'm upgrading, it's -U. H is hash marks, which makes the little pound signs for your processing bar. And V is verbose, which says, let me see what's going on. Okay? So that's what that is. And then right here, I'm just saying kernel here, *RPM, so that way it installs whatever kernel RPMs there are in that folder. Alright, from there I need to install several tools that I will need to compile this. And it has changed as of currently Fedora 17. Now, people who see this video later and maybe in another quarter, it may not match anymore. Because like I said, this keeps changing every freaking time I do this. So it's really annoying. Back when the day, it stayed the same for like 10 years solid and never changed for the routine for how to do this stuff. Now it's changing like every time I do it. It's really frustrating. But it's not like big changes. It's all stuff you could figure out type thing. I did just no time at all last night. I did. I sat with it for a few hours and figured it out type thing. Yum here, install -y so that I don't have to say yes to something. It's the way I like it. XML-TO is needed here. ASCII doc is required also. And I could do yum install space, yum space install space -y. XML-TO, and then same thing over and over again for each one of these if I wanted to, like I did on the LAMP server one. You know what I mean? As opposed to doing these in a list written out like that, I could have done it like this, where I do it one after another like this, but I didn't. You guys want me to format it like that, so it's one after the other? Don't care? Okay. ASCII doc here, and then HM I don't even know what this is, but it told me I needed it, so I put it in there. Elf utils devel, and then this one's real crazy. You must put quotes around this because parentheses are not allowed when you're doing these installs. So if you're going to take a whole group of things, like for instance, don't ever put spaces in the names of your folders and stuff like that. You might go, well, why? Well, because if you do, then you have to put quotes around it every daggone time, and auto-completion doesn't work, and a bunch of stuff like that. So that's exactly what I had to do with this. For whatever reason, someone named Perl with parentheses ext utils : embed, close parentheses, That's how they named it. So because they named it that way, I had to put it in quotes. Otherwise, it goes, oh, you're trying to run a Perl command, and you're trying to do, I'm not kidding you. That's what the problem is. Stupid, but that's what it is. So you have to put it in quotes to make sure to deal with that. So that way it sees it all as one thing and not a series of commands. Because otherwise it does see it as a series of commands. Yeah, it wouldn't matter. It's the parentheses that are a problem. I'm sure these colons are going to be a problem. You know, all that stuff's a problem. So I have to pass it in as one string of text. The only way to do that is put in quotes. So that makes it work. And then I'm going to say RPM build -BP --target space $arc, which gets our current architecture. So that's really cool because that basically what we're doing is we're passing, hey, what architecture do we want to compile this for, or whatnot, and that's what's going on here. So very cool. And then we say kernel.spec. So this is the kernel spec, and it's required. Let's just say that. All right. I'm not going to get into detail on everything. But this $arc basically finds out if you're an i86, 386 type thing. Are you a x86 64-bit architecture, etc. And it basically finds out what architecture your computer is to know what to compile it for. Make sense? Cool. So the dollar with the arc. Right. Parentheses. Yeah. Yeah. Essentially, this is getting that value there. So it's very, very cool. And the target's saying, hey, which architecture are we targeting? And then here we're saying it automatically gets the right one every time when we do it this way. So that's why we're going to use that one. And -BP is just to make it build it. And of course we're going to make a kernel spec out of this. So very cool. Certainly makes life a lot better. Here I'm changing directories to make sure I go into the right place. So I'm doing cd/root/rpm build/build/kernel star, whatever. And it's going to automatically take me into the right directory. Then I do an ls, so that way we can see, hey, what the kernel version is. Otherwise, we won't. And let me prove this to you. All these commands work right out of the box. And when you run the script, does it pause so you see that? I hope. Don't know. I haven't run it. There we are, right there. So you see the Linux here, and it gives you this version. So this is what you see when it does the ls. So now you can see what your kernel version and what the exact freaking name of the thing is. And you should get that there. Going back. Okay, so from there I'm copying everything that's in here, recursive. That's what the -R, capital R is. F is to force it, so that it can keep asking me, do you want to copy this? Do you want to copy that? Do you want to copy this? Do you want to copy that? No, so I don't have to say yes to umpteen different files. And there's umpteen different files, so you'll be here quite a while. There's probably like 100,000 something files here. So unless you want to say yes about 100,000 times, you better put F there for forcing it. V is verbose, so it actually shows you that it's copying it. You don't sit there with the prompt going, gee, I wonder if it's copying. This lets you know that you're copying, okay? And then Linux star here, /usr/src/kernels. Alright, then I echo and ask you for your version number. Well, the version number, I would love to point this out in my documentation every time, is this one right here. That is the version number, okay? So that's what you would put. I point this out because, like, I literally write your version number goes here previously on this, and then people would type in Linux-your version number goes here instead of putting their freaking version number there. So I want to point this out, and this would happen about 50% of the time with students. So it was very frustrating. So and then you couldn't understand why it didn't work, and I pointed out to them, and then they realized immediately. But don't go through this mindlessly. Think about what it is you're doing, because it all makes sense. You just got to think about what you're doing. If you go through the stuff mindlessly, then you're not really going to learn much. So here we're creating the symbolic link, ln space -s. Here the -s makes it symbolic. Of course, ln means link. Here we're saying /usr/src/kernels space Linux dash and star kernel version number. And then it's going to go to /usr/src/linux. And that's pretty cool because that means then when you just cd into Linux, lo and behold, it will take you into the magical directory of lore. I'll prove this. Let me show you where this comes from. C/usr/src. SRC helps if you spell it right? Kernels, ls. Now you can tell which one's ours. Here's all the ones that came from Fedora when we were downloading that stuff for creating the full screen deal when we were installing the software from the VMware. Had to compile down the kernel module. In order to do that, I had to have the source code for the kernel so I could actually get the source code to compile the kernel module, which is aka the driver. Kernel modules are drivers, same thing. So you can see which one's ours though. Ours is Linux. Here, this is the one we have that we're doing. This is our own deal. This is not from Red Hat. So when it's not from Red Hat, it's going to say Linux here, dash, blah, blah, blah. And so we see this whole entire address here. Very cool. If you want, we could even be a little more robust with this, and we could say, hey, before we ask them for this, maybe we should give them a special ls that they would like. Right? And then we could say ls here. And then we could say where we want ls from, and that'd be /usr/src/kernels, right? Ta-da. Make sense? So I'm just showing you the same thing I saw. And then that way they can easily see the kernel version number and determine what to do. And then it's going to ask them to enter in the kernel version number. They could copy and paste it if they even wanted to, or type it in verbatim. Whatever. It's fine, whichever way they want to do it. Right. It's going to read whatever it is they typed. Right. Right. This refers to the contents inside the variable, aka what they typed, which is aka the version number. So it's just going to get appended there. In all actuality, I should probably put quotes around this because it's going to be text. You know what I mean? So I probably should do that number right there just to be safe. But whatever. I mean, I don't have to. We can try this. Let's see what it does. See if it throws a fit at us. Let's find out. The price is wrong. Alright. I'm going to run this whole little routine right here. Well, actually, no, I'm not. Because we already got that. Oh, it didn't like us. Okay. Says, I don't like your multiple lines of copying. Alright, sorry, Mr. Computer there. Alright. So, of course, I could do this right here. So this echoes out. If you ever want to test something, you can do it verbatim, line by line, just by copying and pasting out your script. This is a great way to test stuff too. There's also a way to put it into debug mode. I haven't gone over that yet. I'll do that another day or whatnot, but there's actually some special options you can do to throw the scripts into a debug mode and actually step line by line through the code that you've done, including in loops and things of this nature. It's really great for finding out your issues or problems. It's excellent for that. Read. And so now it's asking me for my number here. And then my number is going to be, well, basically my version number is that right there. Okay, so now it's stored in that variable. And that variable persists only as long as this operating system is running. The moment we restart it, that variable is gone along with the contents. It's not permanent, but as long as we're running in the computer currently here, it's persistent. So, and then the next command will be this one here. Now the problem we're going to have here is that fact that this already exists for me. So I already have the Linux one here. Linux. So it worked. This created a symbolic link that included the $signs. I guess we don't need to put quotes around it. So that proves that. That's what I was trying to establish. And so that created that whole symbolic link. Here we're saying, here's the location of the file that we want to link to. and then this is what this is where we're putting the link and what we're naming it. Make sense? Thus, that's why it's bright. Okay, so now if Linux here is bright blue like this, or whatever you call it, I guess that's bright blue, aqua blue, that means it's a positive, that the symbolic link worked, that it was created properly. If it is black all around it with red, angry red inside, that means it did not work right, and that means you did something wrong. You typed in, you didn't create symbolic link correctly with the symbolic link command. You didn't do ln-s correctly on the command here, so you probably did not type this in right or something like that, and it wasn't able to actually find the actual file, because it actually checks to see, hey, is this a file? You know, remember that -f option where we check to see if it's a file or whatever? Well, it does that, and if that file doesn't exist that you're telling it to link to, guess what it does? It throws up that angry red telling you that, hey, it's not going to work. Does that make sense? It means you screwed up. So there's nothing wrong with the command, there's nothing wrong with the program or anything of the sort. It's an error that you've done. Okay, and then from there, here we have yum install space -y here, and then we have a gtk plus libglade2 -devel here, and then space glib. We're like, why do I need this? Well, this is actually the GNOME development libraries in order to develop GNOME software, and we're actually going to compile and create a program on the fly called gconfig in order to actually, so we're going to say make gconfig, and it's going to literally build the interface based off of the kernel software, off the actual kernel source code on the fly when we tell it to create it. So it's going to build it and run it on the fly. It's really cool. And then this is what it looks like. And then here comes a decent portion of the lecture right here. So I say make here gconfig. Now gconfig is way better than other ones. There's also xconfig, etc., etc. Some of these others, they're command line. You have to literally type in exactly what you want. And once I start showing these kernel options, you're going to go, gee, I would never ever want to type that stuff in. I'm always going to want to do that graphically unless I'm just suicidal or something. And I agree on that. So if I say make gconfig here, I've never ever done it command line. I have pulled it up and looked at it. I looked at it like for 5 seconds and go, oh, no, not doing that. Absolutely not doing that. Nice way of putting it, because it's truly horrible to do it command line. Like, you would have to basically develop the kernel in order to know what options to say. I mean, it's just, there's so much stuff going on the kernel that is ridiculous to sit there and go, oh, I'm just gonna, hand answer every single question. No, you're not. You have to be developing the kernel to do that. I swear you'd have to. All right. So this breaks down to all different categories here, and then we can expand them. And you can literally go through here and tell it, do you want to be either compiled into the kernel, a module, or not compiled at all? Now, modules don't hurt you, okay? Because modules get compiled as separate pieces of software. Basically, they're drivers that sit. And it only loads the modules if the hardware is there. Does that make sense? So it's very flexible. There used to be a way you could do where you could actually compile in all the source code directly into the kernel if you wanted to. And this is faster when you're running it than if it's separate modules. Not a whole lot faster, but a little bit faster. And that would be the reason for doing it. The downside to doing that, compiling all the software directly into the kernel, is the fact that, say your, I don't know, say your NIC card goes out, right? It dies. Whatever. Okay, great. You're like, oh, well, I need to pull out that NIC card and put a new one in, right? Okay, no problem, right? The moment you do that, your operating system won't boot anymore because the kernel doesn't work with that NIC card. And so because it doesn't work with that NIC card, it literally crashes when it gets to that new NIC card, and it can't find the other NIC card that's there. So that would be requiring you to have a whole nother kernel that you could boot up with, and then you'd have to go back and recompile the kernel for that other NIC card and remove the other one from the software. Well, that's a lot of work. That's a nightmare situation, really. And you may not have time. Maybe you need that server up and going right away, and you can't have it down while you compile a kernel. That's crazy. Don't do that. So what you can do is you compile these kernel modules, and then say that hardware dies, no problem. You replace it with a new one. It reads in the kernel module for that new, NIC card, and then it works. So far as flexibility goes, it's really not flexible at all to compile all the software into the kernel. It makes it very stringent. You can't really change anything. Kernel modules are really flexible, lets you change stuff on a fly type thing really easily. You can even load kernel modules later on once you're up and running separately. Basically hot swappable more or less with the kernel modules. You can unload them, you can load them, you can auto load them, all these different things. You can put them into a certain configuration file. I can't remember which one it is anymore because it's been so many years since I've done it. But then you can sit there and tell it to load this kernel module every time I boot up. I mean, it's literally been probably 8 years since the last time I had to do something like that. There was one there was one sound card I had to do it for, where I custom compiled the kernel module. I loaded it, and then I had to code it into one of the configuration scripts in order to make it load every time my computer booted up. For that kernel module. I can't remember what it is anymore, and it's probably changed since back then anyway, so I'd have to look it up anyhow. But there is a way to do that. And so each one of these has information on it. So every time I click on one of these different things, it tells me about it. And here we can see a couple of things. M means module. N means don't compile it at all. Yes means compile it into the kernel directly. Does that make sense to everybody? Okay. Automatic append version information to the version string. If I want this, I can check it. Like so. And it says yes. And sometimes you can't choose module. See the dash here? It's not even an option to be a module or not. It's either compiled directly into the kernel or it's not at all. I want you to change a few things, but be careful what you change on this. Here on the kernel, like I just did this version number, I can't possibly screw it up with that one. There are other things where you could easily screw it up, so be aware of that. And so you need an understanding of how this thing works. I'm going to go over that. Now, normally when I did this at home back in the day, I actually did go through here and remove all the stuff I didn't need and kept only the stuff I do need. I'm not going to require you guys to do that. I'm just happy if you guys can compile it and make it work. So I'm not making this totally real world scenario where you would literally go through and streamline this and compile it down for just exactly what you need and make it run a heck of a lot faster. I'm just happy that if you can make it work at all. So it's kind of what my my deal is on this.
This tool you're using here, if we were doing this real world and wanted to streamline it,
this is how you do it.
and each of those, when you're looking down at the bottom where it explains what it is, that would theoretically be enough information for us to go, okay, I do need this or no, I don't need that?
Yes. You will learn tons by going through this, actually. You won't believe how much you'll learn. And not just about Linux, it's just about operating systems in general and about hardware. And you're just going to learn just bukus of information. This is the paradigm for operating system kernels. Linux kernel is the paradigm. It is the basically set up the paradigm for networking, communications for kernel operations. They have the tightest, fastest code in the world, hands down. Linux has the best. So because of that, it's extremely efficient. I mean, it's written in Objective-C, and it's just really fast. Here's kernel compression modes if we want them. And this one's set with gzip right now. It could be changed to BZ2, which has better compression. Whatever. System B, postfix Q messages. So a certain point to understanding some of the stuff. Let me go over some of this. One of the things I want to go over here, namespace support, yep, etc. Yeah, so we want that. There's so many things here that we could go through. Optimize for size, configure standard kernel features, expert users, embedded systems. This is great if I'm developing an embedded device like a cell phone or something like that. It could be used for something like a TiVo or PS3 or a refrigerator that knows what to order the new milk as your milk is almost out, orders it from the store automatically for you type thing. That kind of crazy stuff. You can do that with this operating system. This is used in third-party devices all the time. Who knows, your watch may be running Linux for all you know. I'm not kidding you. Most people don't have watches anymore because of cell phones. If you own an Android cell phone, you own a Linux cell phone. Android cell phones Android is Linux. It's Linux has a Linux kernel in it. This Linux kernel is in the Android cell phone, and then they wrap it with Java on the outside for creating outside appearance or whatnot. But on the inside, it's Linux. Even the Chrome OS, that operating system, is actually a Linux operating system too. It has a Linux kernel in it, and then they wrapped their Java or whatever around it for the operating system. And it's just Google's front end laid on top of it. But yeah, it's literally Linux underneath the hood. There's a lot of external third-party devices that are Linux for the kernel. Reason why you don't have to pay for a source code. Also, it's extremely tight and small. It's smaller than like anything else out there. It's extremely small. You can really streamline this thing down to squat, and then your kernel source code is like really small. You can put that on a really tiny device and have it run super fast. You don't have to have as nearly as much hardware, and that matters when you're kicking out millions of units, because we're not talking about just, oh, we saved a few $1,000,000. No, you're talking several $1,000,000. You know what I mean? So, and then also don't forget this thing has network capability, so you can have a network-enabled device where it can be updated through the internet for that device or whatever. So, I mean, crazy stuff like that. It could be a heart monitor, for instance, could be running Linux. No joke, where it sends the information back to the clinic and tells them what's going on with that person. Are they having irregular heartbeats or what palpitations, etc., things of that nature. There's lots of stuff that can be done with this kernel. It's crazy powerful. Um, so that matters a lot. Kernel performance events encounters, blah, blah, blah. There's lots of stuff in here, and it changes every time. Do I know what all this stuff does? No, I don't. It changes every time, and I have to go back and reread up on it if I want to really go through and do this. So, and I go through a big learning process every time. You never, I mean, like if you watch this video like some months from now, it's going to be different than it is now. That's all there's to it. Stuff changed. Why has it changed? Because there's new hardware that gets invented. Some of the stuff in here may have not even been released yet. They're developing it still, and they've released it into the kernel for whatever the driver they have for their hardware device they're going to be releasing on the market. That happens too. Realize also companies develop this kernel too, besides just individuals. There's also companies that actively develop it. IBM, for instance, does it. In addition to that, you also have Cisco's branch down here off of Lawrenceville. Was it Scientific Atlanta? Was Scientific Atlanta back when? They've made several contributions and changes to the Linux kernel because they were using it for their set-top devices. Their little set-top devices were running Linux on them. Case in point for embedded systems, right? So we got all kinds of stuff here, and so this is pretty much financed. 75% of Linux open source development is financed by companies because it actually affects their business, and they need to develop it further and better, and it just gets released for free back out into the community, and everybody benefits from it. So this is maintained on a regular basis, like literally update daily. Not kidding. The kernel is updated pretty much daily for new variations and versions. So can we keep up with this? Absolutely not. So you're going to go back through here and look at whatever it is that you're doing every time you go to compile this kernel, because things change. So does it make sense to everybody? Yeah, so there's no way you can have control over it. So yeah, I'm not going to know every little thing in here, and neither does anyone else unless you're developing this kernel. And even then, I doubt they know everything that's going on in this thing. Enable loadable module support. Yes, that better be there. Now, by default, it is checked. That's really important, though, because otherwise you won't be able to load the modules for the drivers for your system. And that'd be stupid not to have that checked. Enable block layer. What's a block? Okay, so this is important. Block is block devices. How many people have ever heard of a block device? Nobody, right? Because you haven't learned much about actual operating systems when you've been on Windows. A block device is going to be a hard drive. It's going to be a CD-ROM drive. It's going to be a DVD drive, a Blu-ray drive. It could be a zip disk. It could be a LS120 drive. It could be a USB hard drive like here. It could be a USB thumb drive. Any drive where you actually save data onto it. Any device where you would actually save data would be a block device. Does that make sense, everybody? So if you have like an external modem or whatever, that's not a block device. If you have something like a keyboard, not a block device, but it's a storage unit. A block device is a storage unit device. It could be inside the computer, it could be outside the computer. Either way, it is a storage device. And that is a block device. So that's important to understand. We have partition types here. Oh, and look at all the different partitions that are supported here. Windows Logical Disk Management, Dynamic Disk Support. If you want it, you can literally turn it on. You have Sun partition tables. Yes, it supports Sun. Karma partition support. EFI GUID partition support. System V 68 partition table. I believe that is a version of Unix. Even Atari table. Amiga. Alpha. I have an Alpha computer from back when. Acorn partition support. I don't even know what that is. Macintosh, PC BIOS, MS DOS partition table support, etc., etc., etc. We can even expand this out. See additional options on this. And we have Minix, Solaris, Unixware, BSD, which is what Mac uses for BSD. So you would want that if you're doing Mac, because it uses FreeBSD. Is what Mac is based on, FreeBSD for their OS. Is a 1978 version of FreeBSD. So.
And the stuff that's auto checked there, default check, that's coming up automatically.
Yeah.
So there's nothing in there that you've already checked.
Correct.
Okay.
Yeah.
Just making sure.
I didn't edit it on purpose, so. But if I wanted to, I could check this one here, for instance. I don't know if that'd be a problem for me to check that or not. Yeah, basically we're going in here and saying, hey, you know, yeah, I need this, I don't need that, etc. Yeah. Right. Right. So you could, no, it's not theoretically. It does make it faster if you remove it. So the best, easiest way to speed up a program is to remove code that's not needed. And it's the most effective method for doing that. Right. Right. You can remove it if you're never going to use Mac partition support. If I do want to access a Mac drive that's been formatted in Mac format and I want to read it on Linux, I can do that if I have this Macintosh partition map support enabled. If I don't, then I can't read that drive or that drive partition. So it's great. Say I'm on a Mac network and I want to be in their format along with being in my Linux format. I can have one drive formatted in their, or one partition formatted in their format, have files saved into that, my Linux can read it and the Mac can read it too. You can do crazy stuff like that with this. I do this all the time where I'll have one partition's basically formatted as NTFS. NTFS is not standard unless you enable it and compile it in. If you do, then you can have it basically formatted in TFS. Windows can see it and save to it and write to it, and Linux can save to it and write to it and whatnot, and basically have a universal drive that you can read back and forth. Because Linux can read over 108 formats or something like that for different operating systems, so it's pretty insane what you can handle. That's just partition types there. We're not even talking about file types yet. I/O schedulers or input-output schedulers. Here's some right here. You can turn those on however needed. Processor types, features. Dynamic tick list system. I don't know much about this. I don't develop processors. Some of this stuff gets down to literally you would have to practically be developing the processors to know some of this stuff, I swear. High resolution timer support. That's great. Really don't know much about that, but whatever. I don't tend to touch this stuff so much. Symmetric multiprocessor support. Okay, so SMP is important, and that is something I want to check, especially with nowadays processors. This is something you pretty much always want on there. And SMP means, well, if you have more than one processor. But think about it, you have cores. And cores are basically multiple processors on a system. So you're multi-core, so this allows it to handle multiple cores, multiple processors simultaneously. I think they're setting it up now to where you can have the cores separately from the CPUs and then have it compute for handling cores as an SMP versus multiple processors SMP, and then broken into two categories. But essentially it's the same stuff. So here's support for SMP with more than 8 CPUs. So in case you have like 16 CPUs in your computer, you would need to turn this on. Of course, I don't need this if I have less than 16 processors in my computer. Make sense? So for most of us, we're not going to be able to afford 16 processors in our computer. I'm just saying. They're kind of expensive when you get that many processors in your machines. Usually the computer's about $25,000 for one of those. They use them on servers, but they're expensive. Also, they eat a lot of electricity and they get kind of hot too with all those processors in them. Support for extended non-PC platforms. Intel mid platform support. Some other stuff here. Lots of other stuff here. There's also special support. Here's multi-core schedule support. So if you have multiple cores, you would need to have that turned on. If you have hyper-threading, which is a feature inside the Intel cores, you would need to turn that on also. So the maximum number of CPUs you're allowed to have on the Linux system is 512. And the minimum that you can have with multiple CPUs is 2. Which makes sense, as it says. So you can have up to 512 CPUs. It'll support that many. Now, I don't think there's a motherboard on God's green earth that can support 512 CPUs, but if it ever exists, it will handle it on Linux. We got fine granularity, or basically scope here. Task level IRQ time counting. We're not going to get into IRQs. We hadn't had to do that in computing. You're setting up your motherboards for the last decade or better. Preemption model. You can actually, voluntary kernel preemption. Preemption kernel, low latency, desktop, etc. You can literally set that up. Reroute for broken boot IRQs. Machine check overheating reporting. Machine check injector, Toshiba laptop support, Dell laptop support. So I mean, they're modules. These are going to be modules. See? Yeah, typically. Yeah. Yeah, it'll change it. Right, first it goes to a check. So now it's compiling it directly into the kernel instead of being a module. Double clicking again makes it nothing at all. Clicking it again makes it to a module. There's nothing wrong with compiling these modules. It's not going to hurt me. If something can be a module, it doesn't hurt me, again, because it doesn't get loaded unless the hardware is there. So I don't lose anything by having it being a module. Right. Correct. Exactly. So yeah, if we had a Toshiba laptop, then it would load the module. Otherwise, it's not going to load that module. So therefore, it's no penalty to us for having this compiled in. Yep. This took me several hours to compile this kernel. It'll take you anywhere from about 2 hours up, pretty much. Here's the memory support. Right now, I only have it set to 4 gigs of memory. Can go up to 64 gigs of memory support. So if you need large amounts of memory supported or whatnot, you can do that. So I can change that if I so desire, right there, like that, to the upper level of support.
That's up to. So if you had an 8 gig,
yeah,
you would want to select 64 gigs.
Right. If you had 8 gigs of RAM, correct. PAE. So this is what the PAE means all the time when we're looking at the different kernels there. We're setting it up. I never heard of this before. This is a newer thing. This is physical address extension support. This is a new feature in the kernels. Yeah, it even says what's new, so it lets you know. PAE is required for NX support. I don't know what NX is. And furthermore, enables larger swap space support for non-overcommit purposes. So it has the cost of more pageable lookup overhead, and also consumes more page table space per process. Okay. So this is great for high memory and things of that nature. Anybody know what they're talking about? Where they're talking about pages, memory, page table, etc. Okay, so RAM is literally broken into pages, as a divisible chunk, and so that's when they're talking about pages of memory. That's what they're talking about. And page table is basically a listing of all those different little partitions of RAM, if you will.
So that little explanation there is kind of telling you what it does and why you may or may not want it.
Right.
Because it says it does this, but it takes more.
Right. Yeah, so depending on what your situation is, depends on whether or not you want a feature. Sometimes those features will speed up your process, and other times it will penalize you. So, having knowledge of this stuff makes a big difference. Literally, just going through this kernel and reading through this stuff will teach you tremendous amounts of information. You will be shocked how much you'll learn by going through this kernel. So I want everybody to go through this whole thing for this. Literally go through all the options and look at everything. Absolutely want that. Because you will learn ridiculous amounts of knowledge. In order to understand some of the stuff, you'll have to look it up. Like, for instance, the page, now you were taught that, or should have been taught that in your hardware course that you had, whatever, for putting together your hardware. But you may not remember all that stuff. Well, all that stuff really actually matters. And now you're getting to see a good example of why it matters, type thing. So having hardware knowledge actually matters quite a bit. And all that stuff you learn, North Bridge, South Bridge, all that stuff actually applies for real. You can't just forget it, type thing. You have to know it. It will actually affect you for doing this stuff. I don't even know. I don't even know what NUMA is. I have no idea. Some kind of emulation. Flat machine to be split into virtual nodes when booted. Wow. Where n is the number of nodes, is only useful for debugging. I'll take your word on it. Okay. Memory model. Apparently we can have several here. Discontiguous memory. New is what it's set to, or we can have sparse memory. So you have different types of memory models here. If we want, we can turn those on. I'm not going to check a bunch of stuff just because I don't want to have a chance of screwing something up. Transparent huge page support. Of course, huge page would mean large amounts of memory for handling that. Things of this nature. Math emulator. If you have such processors that handle math emulations, typically like your 386, 486, they had math emulation on the chips. We don't need that stuff anymore, but back in the day, you had to have a math emulation chip, so we're not going to turn math emulation on. Memory type RAIN register support, so on and so forth. There's tons of stuff here. Buffer overflow, experimental. Avoid experimental stuff if you can. In this case, they have it checked, so they decided it's probably needed. So I'm not going to mess with it, but I try not to do experimental stuff unless I need to. Sometimes I need to, though. Power management, ACPI. So this gets to your power management systems, like your backup power supplies and things of that nature. You can actually interface with them in here and whatnot, and taught to do all kinds of stuff here. Power management debug support. You can have other things like hibernation in here, suspension of RAM and standby support, and runtime PM core functionality, and suspend resume event tracing, and so on and so forth. So you can actually do all these different ones. Advanced power management with the BIOS support, CPU frequency scaling, etc. CPU idle PM support. So you can do all the stuff to handle power saving, which really matters on a notebook computer, but also be useful on a server, if you're not doing squat, I guess, in the background. PCI support, message signal interrupt, PCI debugging. Of course, you know what PCI is, bus, and all that stuff. Yep, it all comes back. So there's all that stuff. Networking support. Everything from amateur radio support. Yes, that's right. You can be your own radio station, or pick them up, or pick up radios, etc. But yeah, literally. Networking options here. TCP networking. So you start to get the idea. Wow, there's a lot of stuff here. Even IPv6 protocol. Network packets, RDS, etc. RDS on Amazon Cloud means database system. So I'm not sure what it means on here, but if it is, let's see here. Datagram sockets. Yeah, it's a good chance this is used for database then. To use InfiniBand and iWarp as a transport. This transport supports the RDMA operations. Okay. Asynchronous transfer mode. Apple Talk, WAN router. Man, yeah. Advanced mesh protocol. There's also wireless, WiMAX, wireless broadband support, RF, etc. Device drivers. Um, Before we reached wireless, there's also in here, and I probably skipped over it by mistake, which is easy to do. There's also a whole thing where you can actually choose what processor you're using. So you can actually select, hey, is it an i386, is it 4086, what type of 4086 is it, AMD, is it Intel, is it, no kidding, what type of Intel chip is it, type thing. You can literally select it and compile it for your computer. So having a list of what hardware you have on the system is key when you're doing this, by the way. You need a printout of all the hardware on your computer. So make sure that you know that, and that's important for doing this when you're doing it. Device drivers. Here they are. Parallel port, plug-and-play support, block devices. Just as a proof, here's a block devices. Notice how they're all, even loopback is considered a block device. But you can get an idea here, hey, this is block devices. Even RAM is considered a block device. Why? Because it stores data, right?
Yeah, when we're doing this on the virtual machine,
Yeah.
it's utilizing. I'm concerned about doing this in the lab versus doing it at home.
Right. So doing this in the lab or at home doesn't matter with the virtual machine because it's just a virtual machine. It's virtualized hardware, meaning it's not real hardware.
But it's emulating whatever it's plugged into the host.
Kind of, sort of, not really so much.
I just don't want to do part of this on one machine and part of it on another, and then having difficulty.
No. It's the hardware is actually virtualized on a VMware, but that does mean that you don't know what the processor is along with the other stuff because it's a fake processor. Right. I'm not going to actually have you guys do any of that stuff. Like I said, I want you guys to do minimal editing. I want you to go through and look through everything. You learn a ton from it, but I don't want you to do a whole lot of editing here because one of the main reasons I don't want you to is because, hey, we're talking about using a virtual machine and no one knows what the actual hardware is in a virtual machine. There's no way of knowing that really. So you can't really go in here and go, oh, it's blah, blah, blah hardware on here. You really don't know that because it's virtualized hardware. So we don't know what it is type thing, quite literally. You will need SCSI support without a doubt. And not just because of SATA. Yeah, you do need SCSI for SATA. But also because all the CD-ROM drives, DVD drives, Blu-ray drives all run through SATA. I mean, sorry, not SATA, but SCSI. Even if it's an IDE, still using a SCSI driver to access it. That's what's going on underneath the hood, and then they do like wrap it in code as a wrapper on it in order to access it as an IDE from there. So it's a wrapper. So in order to use your CD-ROM drive or anything like that, you must have SCSI support installed because it uses SCSI support to do the CD-ROM drives, DVD drives, and Blu-ray drives. It's like, gotcha, you wouldn't know about. I just know this from years and years of doing this. That's how they actually developed it, and so that way they didn't have to reinvent the wheel more or less for doing the CD-ROM drives and such. So I messed a lot back when with burning CD-ROM, all that stuff back in the day when it was early, back in the day when they were first doing it with like XCD roast was like the only program they had is graphical for doing that back in the day. And so I learned all about that stuff in depth back when. And yeah, it does use it underneath the hood. This is what it's doing. No doubt about it. So yeah, SCSI is actually required. SATA or serial ATA, and then PATA is parallel ATA drivers. So if you have SATA or whatnot, you would need this checked. Of course, we don't use PATA, but hey. Here's your RAID and LVM. Of course, we use LVM. If you don't have LVM set up, you won't be accessing our drives. Target core mode here. I don't know much about that. Fusion MP. Triple E. Well, if it didn't say FireWire, that's okay. So yeah, this is the technical name is IEEE 1394 is FireWire. support. Sometimes you won't see it listed as firewall, but they were nice to put the name next to it. I2O device, input output device here. Macintosh device drivers, network support. ISDN, etc. Support, input device support. Now this one might catch you off guard. Alright, well anyways, here's the one for the network support stuff here. Which I think we pretty much went over it earlier though. This is the one that will catch you off guard here. Generic support for input drivers. This is where you get your mouse. This is your joystick interface. It's coming in as a module, so don't worry about it. Don't take it out because it's a module. The mouse has to be compiled directly in. It's required on the system. So you may not take off the mouse, more or less. Let me see if it can get loaded as a module, but I don't believe it can. Yeah, it can't. Alright. And interface debugging. Input device drivers are there. Keyboards. Kind of important. Set with a yes. We got lots of different types of keyboards.
And by checking that first one, it's just saying all.
No, it's just saying keyboards in general, and then you can come in here and check individual ones if you so desire or need to. So you can go in here and say down the list here. They can be compiled as modules if you like, because you did see the underscore there. It's where it has the option to be a module for those. Does that make sense, everybody? Like, okay, so like for instance, this one right here, it can be a module. Check this out. How do I know that? Because there's this dash right here, or underneath the M, where it says, hey, this can be a module. Here, there's no dash here, so it can't be a module. Does that make sense to everybody? So I'm not guessing at it. I know for a fact that's what the deal is. Here's mice. You can even do a 3-button emulation with this stuff, whatnot. It has PS2 mouse back before they had USB mice. Joystick gamepads. Goes all the way back to Gravis grip. Then some. But there's a lot of different ones in here. A lot of support for game controllers. Tablets, like graphics tablets, when you draw on, there they are, including the Wacom tablet. Wacom tablet is awesome. Here's touchscreens. This is cool if you need to like do an installation setup for maybe you're doing networking with a restaurant or whatever, and you're working for a company where they're taking in the financials from the restaurant and doing their financial processing for their day-to-day accounting, and it's part of the whole accounting suite, aka software suite for the restaurants, and the restaurants have this whole menu thing set out where they can sit there and rack up menu items, create new menu items, assign prices to them, and then ring them up, etc. It's all touchscreen driven. Well, here we can basically come in and set up touchscreen on Linux here for doing that, and then we can send the financial information to a database system or wherever over on the company further out. It could be stored in a database system locally and then transferred from that database to another database on a corporate level or something of that nature. So there's touchscreen support. So you may run into that, and that's where it is. You may need that sometime in the future. I do want to point that out because that is something you could encounter. And the way things are going, more and more stuff is going touchscreen. So, yeah, by the way, that's where touchscreen is. It's considered like a game controller / screen, more or less, or a mouse input / screen, if you will. Combo deal. PC speaker support, all this fun stuff. Really has quite a bit of capability for sound cards. It supports a ton of them. Actually, it supports more hardware than Windows does because Windows doesn't support all the old hardware, and Linux does. So like it'll sit there and keep working on stuff that Windows will not even remotely run on anymore because it won't have the drivers. These drivers are still good way later on. So Sound Blaster Live, etc. Sound Blaster Live is old. Some of this other stuff is too. So you could literally have like a 10-year-old sound card and it would work, assuming it still ran. That's the thing. It'd probably burn up by now, but if it did work, the driver is there to literally make it work. So that's pretty cool. You can get a 10-year-old scanner, hook it up, and daggone it, it works. You can get a super ancient old printer, hook it up, it works. It'll be slow as all get out, and you'll hate yourself, but it'll work. Character device, etc. I2C support. So, I mean, just a lot of stuff Here's your power supply class support. Here, hardware monitoring support. Yep. Sorry. So here's your hardware monitoring. There's lots of these. Man, there's a lot of them that people use for doing this stuff. Watchdog timer support, broadband, multimedia support. Here's another good one. Video for Linux. This matters if you're doing video streaming or something like that for an internet web server. So I don't think you're getting away from video. The way things are going with the internet, it's increasing, not decreasing. So chances of you encountering this are getting bigger and bigger and not fewer. DVB, network support, multimedia drivers here, remote controller, etc. Here's video capture adapters. So it's where you have like a webcam or something like that, or a video camera. If you're doing like a higher cost one with that boom mics and all that good stuff, you're recording. You can be recording it and streaming it live through the server. No kidding. Event. Just think about the Olympics, for instance. They're having to literally stream in the data from the cameras and things like that nature, save it into the format, and send it out to all the other networks on the fly on the internet to be rebroadcasted through the internet on a data-driven network. That's all being done on servers. It's not done on a TV station even. Even if they are doing it on a TV station, you still have to store that data into a hard drive or something of that nature. You have to stream it in, record it, handle that. You have a SAN going on in the background, all that good stuff. It's crazy the amount of data you're pumping. So all that stuff matters, and we're going to have more and more of that as it goes along because TV is moving towards the internet. We see that more and more with Netflix, Hulu, etc. There's a bunch of sites that pops up. Crackle. I can go on and on and on. There's a whole list of sites where you can watch free TV basically on the internet, or not free. And it's paid, and it's not much money to pay either. So, virtual video driver here. Memory to memory, multimedia, radio adapters, dynamic TV, blah. Okay, here's graphics support. So here's some of the different graphics drivers. Again, I highly recommend NVIDIA for graphics, period. OSS, this is a standard one for sound. It covers a lot of stuff here. And the Advanced Linux Sound Architecture is another one that's really important. Those two in particular are important, and I use the OSS here for this. And this is how you support most sound cards. You can even have one of those USB sound cards you plug into the back and automatically recognize and work on Linux. Those work on Linux, no problem. It gets detected by this driver here, and it works. Firewire sound devices, USB sound devices, PCI sound devices. See what I'm talking about? So must have USB support put in there, etc., etc. So very cool. We have sound card support. We have USB devices, HID, human. Oh gosh, what's this? Human interface device is what HID is. They may even tell you that, but that's what it is. Yeah, human computer human interface device. Yeah. And this could be several different things, but like this is your input stuff. To computer. This could be everything from like a mouse, etc. Type thing, keyboard, game controller, raw HID, raw input. Input USB devices. Yes, you better check these USB devices so that way you can have USB. Of course, a lot of your HID devices are going to go through USB. But you can see Logitech devices, for instance. Flight systems, controller wheels where you can drive the cars, etc. You got your foot pedals. All kinds of stuff you probably won't ever use on. Here's a PS3 controller. All kinds of stuff you probably never use though. Nintendo Wii. Yeah, there's people that hook up Wii controllers and play them on the Linux. It'll work. You just plug it in. I'm not kidding you. Support the PS3 controller too. Yeah, dude, it supports a lot of stuff. Thrustmaster, I mean, you name it, they support. That's the thing about Linux. It supports so much hardware you just don't realize. It supports far more hardware than the Mac ever dreamed about supporting, or any other operating system. It has more hardware support than any other operating system. That's why I get frustrated at some of these new devices come out and these guys don't write drivers for Linux. You're like going, it's okay. Another person in the community will develop it in no time at all, to the disgruntledness of that company. But hey, if they didn't do it, that company would never support it in the first place. That's for sure. But here we have all these devices with all these kernel modules and such. PlayStation do. Yeah. Sony memory sticks, LED, etc. Hyper hardware. I mean, there's so much stuff. Firmware drivers, file systems. Here's file systems. Here's extension file system 3. Okay. Yeah. You can emulate these other operating systems in Linux that do have emulators for Nintendo. You can run the Nintendo games in it. Same thing goes for Sega and Genesis and the Sony PlayStation 1 and 2. I can't remember if they have a Sony PlayStation 3 emulator or not. They have an Xbox emulator too, I believe. They also have the arcade emulators where you can emulate all the different arcade games. It's called MAME on Linux, and then you can run those arcade games on Linux, the old school ones or whatever. They work on it. You can actually run quite a few games on Linux if you start digging into it, because you can actually access all these different game stations and actually play them on Linux. No joke. Considering you can plug in, you might even be able to emulate a Wii. I'm not sure, but they do have a Wii controller support. But I don't know if they support the Wii itself as an emulator. You'd have to look. Actually, you can just access it in the software installs and see. And also in Ubuntu. Here's extension file system 4 here. This is your journal file system for both of these. If you decide you want an extension file system 3 and then also 2, you can turn them on. So for instance, if I wanted these supported, which I probably would want those supported, I can turn them on. You will have to have security stuff installed and turn on an encryption because it's required, because you have to encrypt your passwords, for instance, on your Linux. So you must have encryption always. Here's JBD debugging support for extension file system 3. You can also add JB2 for extension file system 4. Riser FS. This is a very popular one for a lot of servers. A lot of servers will use Riser FS format. So don't ditch that. JFS is a particular one. I don't ever use it, but it is, I think, popular-ish. XFS is another one that I don't use, but could be very useful for a particular company. Here's some of these others. I've never even heard of some of them, but they got them. We got quota support. Quota, remember, is what happens when they go over their limit for a particular user on a system. So then for you have a quota. And here's your quota support for doing that. So that must be compiled in order to support those limits on the hard drive sizes here. On file system access, etc. Print quota warnings, additional quota sanity checks, old quota, etc., etc. Here we are. Fuse file system, user space caches, CD-ROM and DVD file systems, like so. Here's your FAT and NTFS. If I want NTFS, I literally have to turn it on. Otherwise, by default, like I said, it's not there. We need write support and we need debugging mode. Here's your VFAT. Cool. Pseudo file systems. Here they are. Miscellaneous file systems, including Amiga, eCrypt, Apple Macintosh, Apple Extended, HFS, BIOS, which is a type of Unix, BFS, don't know what that is, EFS, don't know what that is, LogFS, whatever, compressed ROM, this is particular for third-party devices. Things of that nature can sometimes be compressed ROMs. SquashFS, I have no idea what the SquashFS is. We have free here. Minix is a type of Unix. Sonic Blue, OS2, etc., etc., etc. And there's more. Networking file system, NFS. Oh, check it out. Here's NFS. And if we don't have this, guess what? NFS doesn't work. NFS server support. Yep. Right.
But that means if you later down the line you added something that needed NFS support, would you have to recompile in order for that module to get?
Not if you need it later on, because the kernel module will be compiled now. and then when it needs it, it just gets loaded.
So the kernel will recognize it almost like plug and play and say, oh, I need.
Yes, it is plug and play.
I see that because the module's in here, so I'm going to.
Correct. So it automatically detects the hardware, and when it detects the hardware, it automatically loads the kernel module.
Okay, cool.
For you. Yeah. Yep. So, aka the driver, kernel module's driver. Here's CIFS. Remember this from Samba? If you don't have CIFS installed, you can't do Samba, because you won't have support for the Windows file system. So here's another one where this matters. And here's additional debugging routines, etc. if you wanted them. Blah, blah, blah. Postfix, CIFS extended statistics if I want that in there. Ta-da, etc. To mount NetWare volumes. So here's to doing that. Coda file system, I don't know anything about that. Plan or native language support, all different countries, we don't worry about that. Distributed log management, don't really know what that is. Kernel hacking is not what it sounds like. Kernel hacking, okay, so it's quite literally the actual term for hacking and not what's been misrepresented by a bunch of reporters who don't know what hacking is. Hacking means making a patch. Usually this is a fix. This quite literally would be anyone who writes a patch for a company to a piece of software. Say they have a bug in their software and then they need to make a fix to it. They need to make a patch. They need a hack to that software. It's a hack because it's not the actual original software. It's a patch to it. That's why they call it malicious hackers, because these are people who are writing software that is a patch to it, but that, instead of like making it fix something, they actually make it break the system to break through the code or whatnot. They didn't come up with another term for these jerks, so they just started calling them hackers. Hackers already had a name. These were people who fixed software, who made patches to it, software updates. Your software update is a hack. It's a patch. Same thing. They started calling them patches so much because hackers had such bad PR, now at this point. So when they're talking about hacking the kernel here, they quite literally mean hacking the kernel, making patches, making fixes. That's what this is. So this is not, hey, let's break into the kernel and do a bunch of things and take down the system or whatnot. No, this is literally kernel debugging. This is literally coding. This is for hacker developers. These are kernel developers, aka hackers. So that's what they're talking about here, and they are using the term correctly, whereas most people use the term incorrectly 99.999% of the time, it seems like. It's actually kind of frustrating because, yeah, anyways. High memory debugging. Anyways, they have all this stuff in here if you are a programmer who is developing for the kernel. And then that's what this is. So I wanted to point this out so people aren't like freaking out or anything like that. Oh my gosh, you can hack the kernel if I turn this off. No. You have to submit it to the kernel. They do check your code. There's umpteen people checking it, and no, you can't just put in malicious code and have it get by them. It's not going to get by them. Plus, they have a bunch of routines to check for stuff and everything. They know what to look for. You know what I mean? So you can't just do. And in the moment you do that, they're going to know who you are, and they're going to block you, and then you'll never get to submit anything again. So this kernel stays extremely secure and streamlined. Here we have security options. NSA. That's our NSA for this government. That's no BS. That is NSA. Here's their secure Linux that they've developed for it. Okay. Just want to point that out. No joke. That is who developed it. They actually got into a big political heat battle when they released it, and they wanted to pull it back because they didn't want this released. They wanted to have it just for the United States government only and not for the rest of the citizens of the United States. But they're like, dude, we already released it, so you can't really throw a fit about it, which is kind of reason to get it out there. Like, it's already out there now. What are you going to do? So once they got it released, It was great because then people could have it and secure their companies. And this was done to help deal with all the hacking attacks and stuff happening on companies and across the country in order to secure the companies. And this is a effort to do that. So we lucked out, and so this is why Linux is the most secure kernel in the world. Here's cryptographic. Here's the cryptography stuff. And this lets you encrypt passwords and file systems and things of that nature. So this is where you have that. This is absolutely required. Here's your different hash ones here. Digest them. SSH1 is really important. We use this all the time. And MD5 is the other one that's really important. So you need both of those. Without a doubt, you must have both of those. SHA1 is the better of the two formats. But you must have MD5 here also checked. Have to have it. If you don't have it, it's not going to work. The system's not going to work. Everything relies on these two. Okay? So those are an absolute must-have. And then we have ciphers and stuff like that. Keys, more or less, is what a cipher is. Here's virtualization. Here's different library routines. Okay, so that's the kernel in a nutshell. A very quick overview. Save. Alright. And then what I can do is I can ls in here, and I can say vim make file. Alright. And they have a different little name for each one of these kernels. This time is the saber-toothed squirrel. Previously, there's been man-eating seals of antiquity. That's right, antiquity. I can't say it. And whatever. Antiquity. There it is. I finally said it. They've had different ones, usually hilarious. It's very few times where I've seen it where they weren't absolutely just hilarious. So I like saber-toothed squirrel. That works well for me. I can scroll through this. Now, remember, I could grep this too. And I could have easily found this. So, you know, like for instance, I could say, instead of going through here like this, I could say grep here, space, dash I. I think it's, or is it dash I or dash N? I think it's dash N, right, for the line numbers? It's dash N. I is something else. I can't remember. Anyways, make file here. And I think I have to tell it what it is I want to search for first, though. And in this case, I want to do O2, dash O2, to be a little more clear. Okay, let's leave off the dash so it doesn't freak out at me. Alright, so it found it. And it found it on line 248, 249, etc., and even one on 564. So I know where to go look for this now. Make sense? I'm going to change that from optimization level 2 to optimization level 4. So now I know where to go. I don't have to worry about going too far or too slow or whatever. I know I need to go to 248, where here it is. Check it out. We're going to compile with GCC compiler. I'm going to use the G++ compiler because this is C++. GCC is going to be C. And then the flags we're going to use wall, etc. This makes more sense to you if you're a programmer. Missing strict prototypes. And then here's the O2. That is not 02, that is O2 for optimization level. Change that to a 4. Change that one to a 4. Hit escape, shift ZZ. And then I'm ready to compile now optimization level 4. And that will make it run significantly faster.
Alright, so you went into the
make file.
make file, and that's one of the files that's in.
Yeah, the make file is your main file in any software when you're compiling it for Linux or Unix. This is basically the instruction file that tells it how to compile all the software. So that's what a make file is. It's the file that tells it how to make the software. That's why they call it a make file. So it's very well named. It's the file that tells it how to make the programs. It's the make file. And then I just went in here and changed it over. That is not a 0 though. That is 04. That's the key thing to remember. A lot of people get confused about that. That is not 04. That is 04. Don't change that to a 04. If you do, it will not work. Okay. The only reason I know about this is because I actually program on Linux, along with on Unix, and along with Mac, and along with Windows. code on all those different operating systems. So that's how I know about all this. Okay, now going from there, next set of commands to do, which would be the compiling. Now, this is where you're going to love me, because I have essentially I've created the command that keeps you from having to sit around and wait and wait and wait for the next thing to type in, and then the next thing to type in, and the next thing to type in, so on and so forth. If I do this right here and say enter, it's going to literally do each one of these commands in one after another after another after another until it gets it all done. In this case here, make clean is going to wipe out anything that was previously compiled. If you have it failed to compile, you need to do a make clean, because you'll need to go back to that configuration tool I was just showing you. Go back, fix wherever the problem is there, save it, and then go back and do this whole make clean process again. It takes several hours to make the kernel, so every time there's a problem, you'll have to go back and recompile and wait several hours for it to compile. For this, if it's going to error out right away, it'll do it in the first like 15 minutes or so. So I always suggest to people wait around for 15 minutes after you launch the thing for compiling it, then go off, get something to eat, or go do something. The way I've set this up, it'll actually, as soon as it finishes this one command, it then does the next command, which is to make VM Linux. After it's done doing that one, it does the next command, which is make modules. After it's done doing that one, it's going to do the next one, which is makes modules install. After it's finished doing that one, it's going to do the make command. So, and this is how you put multiple lines of commands on the same line by using semicolons after each one. So normally you have to enter this on a line, hit enter, and then it go to the next line. That's why we've been using the semicolon before the then sign every time. Right? We're doing that so we can put multiple lines on the same line. I'm doing it here too with this compiling. So this lets us hit enter and then walk off and leave it. Make sense, everybody? Right, I'm not going to do it now because, like you said, it takes several hours. And I think it took me like 4 hours last night or something like that to compile it. So, just FYI, it takes a while. Right, for the most part. And if it's going to fail later on, it's going to fail way later on, like hours later. So I'm not going to wait around to see it fail later on. So it's going to be waiting hours staring at the screen watching it file. You can do other things while it's compiling, but it is going to eat up a lot of your processing on the system. So FYI, it's going to be slow. But you can actually do your other servers and work on them while you're compiling. You can be working on other classes while you're compiling the kernel. It's perfectly fine. And in here, after we're done doing all this, you're going to do the make install. But in order to do the make install, this has to all go off peachy. No problems, okay? If you have any problems, you have to go. You can't do the make install. You have to go back, rinse and repeat, and whatnot, as far as that goes. If you make it through the make install and it goes properly, it's going to automatically give you the entry inside your grub configuration file. It'll automatically enter it for you. It didn't used to. We used to have to move these files to proper locations and write the grub entry ourselves, or Lilo, which is a Linux loader. Is what Lilo stands for. If you were using Lilo back when, before there was grub, they were competing projects. They do the same thing. But say it all goes wonderfully, no problems, blah blah blah, no issues. What's going to happen now is I need to log off, and then I need to, I'm not sure which one it is actually on the kernel here, but I tested all the kernels and it ran. But I think it's this one right here, that one right there, I think is the right one. I think that's our new one. Because all these other ones are ones from that have been downloaded. Yeah. This one's the only one where I question whether or not that's it. But I really think this is the one that's it right here. So, if I did everything right, this will boot up and the system will work. And I can log in as my user. If I do that, I made it work fine. I compiled it perfectly, no issues, blah, blah, blah. It works. If I can't do that, I go back to the drawing board. And I go back to the make gconfig, reset up the options, recompile back through again until I make it work. Don't select many options. If you do,
There should be a whole lot of re-looking through every single thing.
right,
Because if we can sit there and make notes of what we changed,
right.
then we know what to
Yes,
go back.
please do make notes of what you changed. That might sound like a trivial thing, but it's not trivial. Trust me on that. Yeah, I've had students screw it up so bad that they ended up just chunking their kernel and going back and re-downloading it and re-going through the whole process, because that would be faster and easier than them trying to hunt down the daggone problems for what they did, because they changed so many things and they didn't document any of the stuff they were changing that they had no idea what it is they had done anymore, and they had no idea how to fix it, and it was going to take them way longer to fix it than it was not to. But I got down to back when where I could actually optimize and everything and compile it down in one day, which may not sound like a big deal to you ever. If you really start doing this stuff and really start compiling down the kernel, you'll realize that's really freaking fast to do it in one day. Some other people might take them a week to do that, working at full time, not doing anything else, just kernel. I mean, it's significant.
Now, if it didn't work, it looks like it's working and you're able to log in.
I just mistyped my password. Go on.
But if it doesn't work, then we're going to reboot and select a different kernel.
If it doesn't work, you have to go back to the make gconfig, do all that.
If it doesn't work, you're not able to get into the system.
Right, you'll have to go back and select a different kernel. Yeah, because I was running on a different kernel when I was compiling that kernel. So on and so forth. Same thing, same idea.
So we need to know which kernel we're using to begin with.
Well, any of those kernels that we download and installed should work. But ta-da, here it is. And it full screens and all that good happy mess. But there we are. And that is a working kernel. That's 100 right there. Any questions?
How do we submit?
In order to submit, my favorite way to do this is for you to take screenshots of you booting it, where it load up screen where you're selecting the right kernel, and then a screenshot with system monitor would be ideal. This is the system monitor I'm looking for. Please be the system monitor I want. Please launch. This is not the system monitor I'm looking for. There's another one. They do have it. This one isn't it, but it actually gives you all the information about the system, including what kernel you're running.
And you want us to upload our script as well?
Yes, please upload the script as well. Yeah, because that'd be nice. I'm gonna go to applications. I can probably find it through here, assuming they haven't taken it out. I don't know all they've done on 17, so you know how that goes. But let's dig through here real quick. Yeah, see, they have two different system monitors. There it is. That's the one I want. The first one out of the two of them. Isn't that confusing, guys? But yeah, it literally tells me what kernel. See that right there? Give me a screenshot of this if you're logged in here, and I know which one you did. Makes sense? Yep. Yeah, the login screen where I was selecting the kernel there, when we boot it up wherever, take a screenshot of that, take a screenshot of this right here with it set to system right here like this, and then upload the script.
Will it let you screenshot at that? Or you're going to have to do it through the host?
Yeah, you might have to do it through Windows. The Alt Print screen will let you do that. And then paste that into either Photoshop, or you could do it into MS Paint or something like that. Save it out from there. That'll work. Yeah, you wouldn't be able to screenshot inside of Linux like you normally do for that one. I wish, but no. That's all I need, man. Yeah, you could have it where it does all that stuff going up to the make gconfig part. Um, Once you get to the make gconfig, don't run to that part as a script. Like break that out separately. I just did as a list of commands to show you all the steps or whatnot, more or less. Could you write it as a script and actually run it? Yes, you can. But when you get to the make gconfig, it's fine if you want to even make it run the make gconfig command, but you need to stop right after that and make that as a separate script. All right, so he was asking, what can we just run that whole thing as a script? And I said, no, not the whole thing, but a part of it for sure, and the first part of it. And the reason why, again, is because you're going to get into an issue where you would need to be logged in as root ahead of time. So you have to do this su -- first before you do this. But yeah, you could literally come in here and just run this, and it should go through and do all this. Make sure it's doing it though, because I haven't really tested it, so I can't tell you that it did it. So it'll go through all this stuff and through here and the make gconfig, and after the make gconfig you need to stop because this is going to get into this make thing and it'll launch this make probably before this make gconfig is done. I don't know, I haven't tested it, so it's very possible it could run the make gconfig and then start trying to compile it while you're in your make gconfig, which is not something you want. You can only compile once you're out of the make gconfig, and so I don't know what kind of issue that's going to cause for the script or not. Again, I haven't run that, and I don't know what's going to happen type thing. Yeah, cut off at make gconfig. So then it'll go through all the installation process, ask you for the version number, you pop in the version number, then it goes through, installs the rest of the stuff, launches the make gconfig screen for you automatically. You say save, and then you run this thing here. Yeah, that's the rest of another script if you wanted to, yeah, or something like that. And then do the make install from there. I mean, you can try it. Hey, maybe we get lucky and it holds this process until we're done with the gconfig. Then you say save, it automatically exits out of that process, and then it continues on from there. But I wouldn't count on it. It could go either way on that. I don't know what's going to happen. Yeah. I mean, who knows literally what's going to happen. Yeah, you may need to break it into two scripts, literally, if you're going to do it as scripts. I'm going to run it as such. I mean, can you? Yes, you can. But those are the commands essentially for making this happen, and that's just what I was wanting to show.
So, yeah, you can do it all outside of a script and just do each command separately.
Yeah, you can do it all outside of a script and just run these commands separately, individually, in the terminal. Copy and paste them, or you can type them in. Either way. Right. Yeah, because once you've typed out the script, I'm happy. I'm good to go. Because that means basically you've typed in these commands. And I did these with absolute path, so that way people don't get lost where they are in the directories and then type in the wrong thing, make it work. So I made absolute paths on purpose, so that way there's no chance for you to screw it up, more or less. I'm glad you're doing PWD because I have a lot of students that don't do that, and that happens most times than not. Yeah. See, that's exactly what you want to do. That's smart. That's what I want you to do. Yeah, when you get stuck and you're like, oh, what? I don't know what's going on. Why isn't this working? Type PWD to find out where you're at, and you don't realize you're not in the right place. So, but you have to be able to think through what you're doing in order to do something like that. And I've had too many issues where a large number of people don't CD into the right place, and then things don't work because of it, and they get really frustrated. Sometimes they get kind of vile with their comments, so I just make an absolute path so I don't have to deal with them. Not anyone here, but I've had in the past. I've had some people get pretty down and really rude on it, and it's their own mistake, but they don't see it that way. So, but yeah, that's how you compile your kernel. And realize while this is compiling, you can work on your other servers or other projects or other things while you're doing it. Yeah, we have till the last week. Yeah, end of class on the last week. The moment, okay, yeah, and by the way, everything's due on the last class in that class. Everything. If there's anything you don't have done that was still could be done by that time, then it has to be turned in then and not a moment later. Like, oh, I'll turn it in tomorrow. No, no, you don't. I close the class out, submit it for grace to the headquarters. It's over with. Okay, so no, the class is literally over with right then and there. Yeah. Any questions? Oh, a lot of questions, but not involving this. Okay, well, that's a whole nother ball game. All right, let me stop this.